Question 2, we've got a binomial distribution problem. We've got a machine that packs sweets, and a seventh of the sweets contains a prize. So these packets of sweets, both with a prize and without a prize, are packed into boxes of 40 each. We've got a random variable t, and that represents the number of packets that contain a prize. State a condition needed for t to be modelled by the binomial distribution n is equal to 40, and the probability is a seventh. Well, one obvious condition that needs to be satisfied is that the events, in other words, picking a packet, has to be independent from the next event. In other words, if you pick a packet and it contains a prize, you mustn't keep it, you must put it back into the selection so that the next pick can have the same probability. So here is that written down. So part B. And here is our distribution, and we've been asked to find the probability that the box of 40 contains exactly 6 packets. So if we want the probability that 6 packets, exactly 6 packets, contain a prize, P6, we need to use the binomial probability distribution function on the calculator. And the calculator needs that value of 6, and it needs n is equal to 40, and it needs p is equal to 0.1428, or 1 over 7. Hitting equals, we get the probability that 6 is equal to 0.1727, and on it goes. And that's the answer to part 1. Part 2, we need fewer than 3 packets. Well, fewer than 3 packets is 2 packets. And this time we need the binomial cumulative distribution function. So given that the number of packets n is still 40 and the probability is still 0.1428, all we need is x now is equal to 2, which means it will calculate the probability of getting no packets, 1 packet, or 2. And if you push equals on the calculator, you get an answer of 0.615. So we've got a slightly different situation now. We've got 5 boxes, and they've been bought, and we need to find the probability that exactly 2 of the 5 boxes have fewer than 3 packets. Now, fewer than 3 packets is the probability here. So the probability that we're now working with is equal to 0.0615. N this time is equal to 5. And we need to find the probability that exactly 2 of these boxes, so it's not a cumulative distribution, it's a probability distribution, of exactly 2 of the 5 boxes contain a prize. So our variables are x must equal to, the probability is 0.615, and n is equal to 5. Okay, popping that into the binomial PD function on the calculator, and you get an answer that the probability of exactly 2 is equal to 0.0313, and on that goes. And that's the answer to part C. So in part D, we've got a challenge to the probability that the prize ratio probability in the boxes is a seventh. And Camille claims that the proportion is less than a seventh. So we've got an established null hypothesis of a seventh, and we're now claiming that the new hypothesis is less than a seventh. We've got 110 packets taken and 9 contained the prize, and we need to see whether at a 5% significance level this result would support the hypothesis that the probability is wrong. So let's set that out. So here are the 2 hypotheses. The null hypothesis is that p is equal to a seventh, and the new suggestion is that p is less than a seventh. So we've got the number of packets being tested is 110. We're going to assume for the moment that the probability is a seventh, and the result of the survey is that 9 of the packets contains a prize. So using the binomial CD function on the calculator, then I'm going to calculate the probability of our value of the number of successes is less than or equal to 9. And I get an answer of 0.03829, and on it goes. So now we bring in the 5% significance level. Now 5% is 0.05. But our answer is lower than that, so we are in the lower tail of the distribution, which of course is the danger zone. So there is enough evidence that the probability of finding a prize is indeed less than a seventh. So there's the answer written down, that as 0.03829 is less than 0.05, which is our 5% significant level, there is enough evidence to challenge the null hypothesis, and that P, the probability of getting a prize, is indeed less than 1/7. And that's the end of the question.